Good morning. We finally arrived to the moment where we can derive a simulation model for the helicopter longitudinal motion. We are going to derive today a helicopter model, simulation model, in a 3 degrees of freedom system. What are the equations of motion for a longitudinal plane of a helicopter? You have first to recall the fundamental equations of dynamics. The longitudinal motion is of course involving the horizontal velocity u, the vertical velocity w, and the pitch rate q. And this is the fuselage, the pitch of the fuselage. These are the fundamental equations of dynamics that you have learned in the third year. Therefore, we will have to now find the forces and moments which are acting on the helicopter in a body system of reference. For helicopter, you remember that we had more system of reference that we could see the motion. We had the so-called tip-off plane, which is the plane formed by the blade tips. We had the shaft plane, which is the plane perpendicular to the shaft hub. We had the non-feathering plane, which is the plane where an observer sees no variation in the cyclic pitch. And we have the control plane, which is the plane containing the swash plate. So, assuming the body system of reference parallel with one of these planes, it will result in a certain motion, in a helicopter motion in that system of reference. For the case that we are going to study, you have here. You see at the moment the helicopter, and you see that the helicopter is having a horizontal velocity, a vertical velocity, and a pitch rate. And here you see what is happening with the rotor disc. If we are in a shaft plane, we are inputting a pitch motion, so we move the blades to the theta c, to the control plane, and what is happening? The plane will, the rotor plane will blow back. So finally with a lateral disc tilt A1, so that the final equilibrium position will be with respect to the disc plane. In this way, we also have the angle of attack of the disc in a disc plane, in a control plane, and of course, or in a shaft plane. The fuselage tilt is, of course, equal with the pitch of the fuselage, and usually is taken with a minus as it is under the horizon. So, what are the equations of motion in a 3 degrees of freedom? We have to project the Fx, Fz, and Mi in this system of reference that I described you up. So there is a component of the weight, the drag of the fuselage, and the thrust. In the z-axis, again, the weight, fuselage, and the thrust. So do not forget, we consider the helicopter shaft plane as the plane of reference. And there is an aerodynamic, a pitch moment, which is, if you look back at the figure, if the rotor is situated at a distant h from the body, from the CG of the helicopter, the moment will be a t sinus of angle theta c minus a1. Now, these are the forces. If we have the forces, and if we do not forget that actually the fuselage pitch can be expressed as a function of the velocities, substituting 2 to 4 into the initial equation of motion will result into the helicopter equations of motion in a 3 degrees of freedom longitudinal model. You see that the motion is depending on the drag of the fuselage, on the thrust force, and you see also the cyclic pitch, longitudinal tilt, and here only the pitch rate. The thrust force, we have a special lecture where we are going to determine the thrust force of the helicopter in forward flight. We will use for this the blade element theory and the Glauert theory. So, how to simulate the model? Building a flight mechanics model for piloted simulation. The scheme that you will have, it is in the lecture notes on page 95. This scheme, it will be explained in this lecture. I will go straight to explaining the scheme. We will have initial data for the helicopter. The moment of inertia, the drag coefficient, the radius of the helicopter, the RPM of the helicopter, and so forth. We will know at a certain moment the collective pitch θ0 and the cyclic pitch of the helicopter. And we will have the state variables which are according to the 3 degrees of freedom model, U, W, Q, and θf. The first thing that you have to do is to initialize these parameters, and then you have to start calculating the parameters that you need for the equations of motions. So you will need the total velocity of the helicopter, which is simply a square root of the horizontal and the vertical velocity. You need the angle of attack with respect to the control plane. Be attentive here. So you see, this is just the cyclic pitch. Be attentive in what quadrant you are. If the helicopter has a velocity horizontal smaller than 0, you need to stay in a good quadrant and add a P. You can calculate, if you have alpha C, you can calculate the advance ratio of the helicopter on every moment and the component which is perpendicular to the control plane. Then you will need to calculate further the induced velocity of the blade of the helicopter and also the flapping angles. How? You will start entering into an algorithm and until you obtained this induced velocity. First, you have to express the flapping longitudinal disk tilt. We already derived this longitudinal disk tilt. You can calculate it on every moment. And we have also derived the thrust in a blade element theory and in a Glauert theory. The idea is that we consider a function which is now a function lambda induced velocity, which is a difference between CD blade element minus CD Glauert, and we are going to choose the induced velocity lambda e till this function is 0. So till these two formula are equal. When you are out from this algorithm, it means that you will have the induced velocity on that state, the longitudinal disk tilt, and the thrust coefficient of the helicopter. Now you just have to go into the equations of motion. So the drag of the fuselage can be calculated. All the terms in this equation of motions can be performed. And you have to go in a loop. Every second of the motion, you have to integrate the equations, usually with an Euler. It is enough, and then find the new states of the helicopter and go back and calculate again in a closed loop. This is actually the main logic of 3 degrees of freedom longitudinal model that you will have to build into a simulation model in MATLAB or Simulink or in what language you prefer. This ends this course of flight mechanics model.